Well, hello, my good friends. Welcome. Today's a very special lesson. I've been waiting to do this one for a while. Actually, you get to use your imagination in today's lesson. And so hopefully you chuckled at that because today we're going to be talking about the imaginary number. So get yourself something to write with and we're going to get started. And as you know, thinking should always be paired with writing, because writing actually gives form to the thought and makes a record of it so that you can rethink that thought later as precisely as you thought it now. So let's begin. Share my screen with you. Here we should have the square root of 25 here. Now from basic math, that's fairly simple. I mean, 5, right? Not a big deal at all. What about the square root or the negative of the square root of 25? You say, well, that's equal to negative of 5. So there's my answer. Pretty nice. But then what was the square root of a negative 25? Now, up until now, you've been like, no, you can't do that. This is not real. That's not a real number. Because it's really asking what squared is equal to negative 25. And of course, there isn't a real number that when you square it, you get negative 25. Some silly like 6th grader or 7th grader is going to go, oh no, it's negative 5 squared. No, negative 5 squared is negative 5 times negative 5. And what's a negative times a negative? Positive 25. Oh, okay. So even negative 5 doesn't work because when you square it, you get 2 negatives, and a negative times a negative is a positive. Why? Can you answer that? Can you tell me why a negative times a negative is a positive? You think about that. Write me something in the comments. Anyway, so this up until now has been a problem, but now we're going to resolve that. Okay. The imaginary number. It's very, very simple. The imaginary number, which is I obviously for imaginary, it's a number like pi. It's not a variable. It has a defined meaning. Make sure that when you draw an I, you put like a little hook on the end of it so it doesn't look like a 1 or something like that. But I is defined as the square root of a negative 1. There you go. The square root of a negative 1, that's defined as I, the imaginary number. Now, it's not real, and so anything that isn't real must be imaginary. And of course, mathematicians are using the terms real and imaginary differently than perhaps the meaning of those words have in just normal conversation. So that's an interesting thing. So like, I wonder if pi and I would ever have a conversation. What would they say? I think I know what they would say. Here we go. Let's have just a little fun with this before we get in. Pi would say to I, get real. Because the imaginary number is not a real number in the mathematical sense. And I would reply back, be rational. Because pi is not a rational number. Like, they're telling each other to do things that are impossible for them to do. So anyway, that would be the conversation that they would have. All right, back to the idea now. No, the imaginary number is just I. So that means that I squared, if you were to square I, that's equal to negative 1. Okay, so there is a number that you can square that you wind up with a negative as an answer, and that would be the imaginary number. Let's see here. For example, if I did something now like this, if I said the square root of negative 25, we now have a way to address this. Square root of 25. Can I say that that's equal to the square root of a negative 1 times a positive 25? Yes, I can. Now, because of the properties, the product property of radicals, we know that we can take a square root of a product and make it a product of square roots. So this is going to be the square root of -1 times the square root of 25. And now we can say that the square root of -1, well, that's the imaginary number I. And then the square root of +25, we already know that, that's 5. But that's a weird way of writing it. From now on, we're going to write it like this. We're going to write it like 5i. That's how you're going to be required to write it. And you can treat I just like a variable in the sense of multiplying and adding like terms and things like that. So then how would we do something like the square root of -18? Well, to simplify things, I'll go a little faster. The square root can come out of the radical as an I. Now, what do I do with the square root of 18? You say that that would be like 9 times 2. And the square root, or 9, can come out from the square root as a 3. So my final answer to this then would be 3i times the square root of 2. And that would be how you would write down an example like that. Okay, so let's do some exercises now. So example number 1, the square root of -27. All right, so I've got a couple things here. I've got a negative sign underneath the radical. It's a square root. And then 27 itself is not a perfect square, but I have a factor of 27 that is. So the first thing I will do is I will pull out the negative. That comes out as an I square root of +27. Now 27 can be broken down into a 9 times a 3. So then the 9 comes out, the square root of 9 is a 3. So that becomes 3i times the square root of 3. Okay, and that's as far as you can go with it. All right. Let's see this one here. Oh, I don't really have much of an instinct for that one. Although the negative can come out as an I times the square root of 216. I don't like have that memorized. Where's my machine? I'm going to see if I can rewrite this as something that's a factor of a perfect square. So what are the perfect squares? Well, the first one is 1. 1 squared is 1, but that does nothing for you. So let's do 2 squared is 4. So let me do 216 divided by 4 and see if I get an integer value. Oh, I do. It's 54. But I feel like there's something else in there. Let me see if I can find the largest one. So 216, the next square would be a 9. So divided by 9. It's 24. So that one works as well, but I still feel like I can get a bigger one. So let's do 216 divided by, what was the 4 squared? 16? Not an integer, not a whole number. So 216 divided by 25. I don't think that'll work. No. 216 divided by 6 squared. 36. Oh, there we go. 216 is equal to 36 times 6. Now, one of those is a perfect square. Which is it? 36. 36 comes out as the square root of 36. So what is the square root of 36? 6. So this becomes now 6i times the square root of 6. That would be as far as I can go with it. Okay? So your imaginary value I then is going to be written after the coefficient of this 6 right here, then I, and then the radical last. The reason to write the radical last is because you don't want any ambiguity as to how far that symbol goes. Like if I had written it like this, if I had said 6 square root of 6, and then an I right there, is the I under the radical? Is the I outside the radical? It lends itself to some confusion. 6, the square root of 6 with a little hook on the end, tells you where the radical ends. Maybe that would be okay, but this one here is the best way to write it. Okay? All right, so now, products. What is -5i times 3i? It's not a decimal point, but even then, maybe parentheses would help us see it a little bit better. How would you do -5x times 3x? Because it's the same idea. Okay, I would do the coefficients first. -5 times 3 would be -15, and then x times an x would be x squared. So let me do that here. -5 times 3 would be -15, and then I times I is I squared. But I squared can be simplified, whereas x squared cannot. Do you remember what I squared is? -15 times, what is I squared? negative 1, right? Because isn't I equal to the square root of negative 1? And then if I square the left and square the right, I get I squared is equal to negative 1. See, there we go. All right. So now I can further multiply this. Negative 15 times negative 1, positive 15. There we go. Nice. You couldn't do that with the x's because you didn't know what x was, but you do know what I is. And by the way, let's go ahead and just kind of make a little bit of a list. Shall we do that? Where shall we do it? Maybe we should just do it up here with the imaginary number. I squared is equal to negative 1. What is I cubed? Is that not I times I squared? So isn't that equal to a negative I? Because I squared is a negative 1. What is then I to the fourth? I to the fourth is then going to be I squared times I squared, which is equal to negative 1 times negative 1, which is positive 1. What is I to the fifth? That's equal to I to the fourth times I. So that's equal to I, 1I, right? Because I to the fourth is 1. And the pattern just kind of repeats itself. We're back to I now. So you can keep going with this as far as you want to go. Let's go back now and do that next example. This one's curious. Now, the wrong way to do this is to do the multiplication of the radicands first. Remember the inside here? This is called a radicand. And we know that if I have the square root of a multiplied by the square root of b, I can say that it's the single radical of a times b. We did that earlier where we went backwards. We took the bottom one, a multiplication, and made it a product of individual ones, okay? Now, if you did that, you would get negative 6 times negative 15, and the negative would cancel each other out, but that's wrong, okay? You need to do the imaginaries first. The negatives here don't cancel themselves out like they would if you were just multiplying negative 6 and negative 15. So let me do the imaginaries first. The negative comes out as an I times the square root of 6. And then that multiplied by I times the square root of 15. Okay, do you see that now, how I've simplified out an imaginary from the radical first? Then I can now multiply the positive ones together. So let's see here. But first, let me do I times I. What's that? I squared. And then this becomes radical 6 times 15. What is that? 60 plus 30. Well, it looks like 90 to me. Is that right? I think that's right. Now, the i's are taken care of. I've got the imaginaries out of the radical. And so now I can simplify what's inside the radical. Isn't 90 9 times 10? And 9 is the perfect square root. Okay? So now what I can do is I can simplify I squared. I squared, what is that? That's negative 1. And then I can simplify the square root of 90 as 3 square root of 10. And now let me put them all together. Negative 3 square root of 10. There we go. And the I squared then was the thing that was responsible for that negative sign. If you had multiplied these straight together and gotten the positive, because a negative times a negative is a positive, positive 90, you would have gotten a positive 3 square root of 10. But it wasn't positive, it was a negative. The imaginaries, two imaginaries multiplied together makes the thing negative. So you got to take care of the imaginaries first. Alrighty? That's pretty good. The square root property. Okay. Now, we're going to use, we needed to do this imaginary number thing because we're going to start solving some more quadratics. And when we do that with some negative answers or some negative values, you'd have to have imaginaries. Okay. So the square root property really isn't a property involving imaginary numbers directly, but we needed imaginaries before we could then do this. So the square root property basically says if I have something like x squared equal to some number here times c. C is just some constant. Okay. If I square root the left-hand side and I square root the right-hand side, the square root and a square are opposite inverse operations, right? They cancel each other out. So on the left, I would just get x, and on the right, I would get positive and negative the square root of c. Hopefully you learned the positive and negative in Algebra 1. The reason why you got a positive and a negative is because you get two different answers. I don't know why, like I don't know why in the world you would think that you would ever get two different answers, but that's a subject for another time. But you have to isolate the square before you can square root it. So for example, let me do something over here as an example. Let's do example number 1. And this is just kind of like me kind of doing something off the top of my head here. If I had something like x squared is equal to 25, then I would square root the left and I would square root the right, and I would get x is equal to positive and negative 5. Why is that? Because the original value was what squared is equal to positive 25. What? Well, both a positive 5 when you square it works, but also a negative 5 when you square it also works, and that's why we get two different answers. Okay? Now, what if you've got some other clutter in there first? What do you mean? Well, what if I had something like this? Let me see if I can make something up here. What if I had 3 x squared minus, I got to be thoughtful here, minus 5 is equal to 22. Remember when you solved equations, you kind of went backwards from order of operations. Order of operations would be parentheses, exponents, multiply, divide, add, subtract. And when you simplified, you went this way. When you solve equations, you go the other way. I need to take care of things that are subtracted and added before I do multiply and divide. And before I do exponents, I have to take care of this stuff. So I really can't square root. I can't square root the entire left-hand side here and the entire right-hand side here. I have to get the x squared package all by itself first. So let me do this. Let me subtract, add 5 to both sides, plus 5. This cancels. 3x squared is equal to 27. Now I still don't square root both sides first. I'm going to divide both sides by 3. Divide both sides by 3. Cancellations. And so now I get x squared is equal to 9. Now I can take the square root of both sides. Okay? So you've got to isolate your squared thing before you square root it. Okay, so now how does that work with something like this? Solve x squared plus 64 is equal to 0. Okay, I need to isolate the x squared. How do I do that? I would subtract 64 from both sides, minus 64. This cancels. X squared is equal to negative 64. Now do you see where it's going to require the use of imaginary numbers, right? Now that I've got my squared thing isolated, I can square root the entire left-hand side and I square root the entire right-hand side. Okay, x is equal to plus or minus. You got to always put the plus or minus in there. Oh, what is the square root of negative 64? Well, the negative can be an I, and the 64 can be an 8, although that's in awkward order. X is equal to plus and minus 8i. I'm comfortable with you leaving it like this. But remember, you've got two answers. You've really got positive 8i and you've got negative 8i. And for the life of me, I still have no idea why you would have two answers. Was there another one? I thought maybe there was another one. Oop, no, I guess not. Okay. Complex numbers. All right, complex. Like maybe if you're doing I don't know, relationship status on social media, and it's it's complicated. There's more than one thing involved, sort of. There's more than one consideration. Complex numbers are numbers that are both real and at the same time imaginary. Okay. Up until now, we've just been doing pure imaginary numbers. Okay. Positive 8i, negative 8i, okay? But what if you're going to add a real part to it? Complex numbers are always written in this form. A plus b times I. And a and b are just constants. This part right here is the real part. This part right here is the imaginary part. They've always got to be separate things. And the imaginary value always has to come after the real value. Okay, that's just the standard way of writing them. It's not like technically wrong if you write it backwards, but it's like format wrong. Okay, so for example, I might have something like 3 plus 5i as a value. The 3 is the real part. And the positive 5i, notice the sign goes with the 5, is the imaginary part. Okay? So, what would you do? Well, if you had something like, I don't know, 15i minus 35 all divided by 7. Okay, I understand what that is, but it's not in complex form. The first thing that I need to do is I need to make, I see an imaginary part. I see an imaginary part right here and then a real part right there. The first thing I need to do is split them into two different parts, okay? So this is now going to be then 15i over 7 minus 35 over 7, okay? But now the imaginary part needs to come after the real part. So I'm just going to swap those two pieces. And can I do negative 35 divided by 7? Wouldn't that just be 5? So this becomes negative 5 plus, because there's a plus sign there, even if it's not written, okay, plus 15i over 7. Almost done. I'll come this way. Negative 5 plus 15 over 7 times I. The way that you do it is you really need to separate out, you need to separate the b from the I itself. Okay, just remember that I goes in the numerator. It's I over 1 if you wanted to do it that way. But don't ever do that. That's silly. I'll call you a newbie if you do that. Okay, so now add and subtract complex numbers. These things, they work just the same, like I said, as a variable. You treat it just the same in terms of the rules by which you combine and multiply and stuff like that. But you can simplify things because I squared is negative 1 and I cubed is negative I, stuff like that. You want to reduce the exponent of your imaginary number as much as you can. So for A here, 5 minus 7i plus 2 minus 4i. 4i. I used to get called 4 eyes in school a lot because I wear glasses. You ever heard that called 4 eyes? 4 eyes, like 2 real ones and then two fake ones. Actually, I guess technically now you can call me 6 eyes because I got bifocals in here. But anyway, enough of the jokes. Okay, so I really don't, since it's plus, I don't really need the grouping symbol. So it's just 5 minus 7i plus 2i plus 4i. And let me do the real part first. A 5, oops, I threw an I in there. Just so excited about I's, I threw an I there. 5 plus 2, that's going to be 7. Those are done. And then a negative 7i plus a 4i, that's going to be a negative 3i. And that's as far as you can go on that one. You obviously can't combine them because they're not like terms. Like terms have the same variable and the same coefficient or the same thing. Like 7 doesn't have an I. Done with that one. But this one now, when you subtract, you do need to pay attention here because it's minus the group. So I have to distribute that negative. Distribute the negative. And usually I'm an optimistic person and I don't like people giving me their negativity. But in algebra, it means something different. So I'm going to copy down the original 4 minus 8i, and then a negative times a positive is going to be negative 3, and then a negative times a negative, positive 6i. And then I'll group my real stuff together. 4 minus 3, that's going to be a 1, and then a negative 8i plus 6i, that'd be negative 2i. That's as far as you can go with that one. How would you multiply? Same way that you would do it with an x. Okay, it's all the same thing. Distribute each term in the first binomial times each term in the second one. You can call it FOIL if you want to on this one. Maybe you've heard of that. I really don't like FOIL as a phrase because it only works with binomials. If you have trinomials, you can't FOIL because this, anyway. Negative 6 times 3, negative 18. Negative 6 times negative 3i. Positive 18i. And now I'm done with the 6. Now a negative I times a 3. Negative 3i. And then a negative times a negative is a positive. The coefficient on the I is a 1. A 1 times a 3 is a 3. But then don't forget this one. Look, 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 look. I times I squared. All right, so now let's clean it up a little bit. Negative 18, done with that one. Negative 18i minus 3i. Wasn't that going to be positive 15i? Oh, but wait. What's an I squared? Isn't I squared equal to negative 1? So when I cancel this, I can change that to a negative minus 3. And now I don't have any i's on that term. And so I got to list a little bit more to do. Negative 18 minus 3, negative 21. Yeah, okay. Plus 15i. There we go. Okay. Complex numbers, you do it just the same way that you would any other variable, except when you get down to i's with higher exponents than 1, you have to simplify them down. So there's just an extra step there. Oh my goodness. Yeah. Rationalizing denominators. I could preach on this for a little bit. You need to know how to do it. This is probably going to show up on like an ACT test and something like that. Let's do a simpler one first. This is oftentimes it's division of imaginaries, but really it involves more than that. It's more than just dividing. If I did something like this, if I had maybe 3i divided by I, you could cancel those out and just call that 3. Okay, because it works the same like an algebraic variable. If I had something like 5 plus 2i all over I, you could say that that's, whoops, I didn't mean to shift. You could say that that's 5 over I plus 2, but you still have an I in the denominator. One of the kind of the rules in formatting of math is that you need to have a rational number in the denominator. So no square roots and no imaginaries, because neither one of those are a rational number. So maybe if you remember in Algebra 1, rationalizing the denominator with a square root, okay? Yeah, I wish I could talk more on this. Maybe I'll shoot a separate video on why that's done and why oftentimes it's not as necessary as it used to be. But anyway, this doesn't really help out a whole lot. So what do I do with this one? Well, remember that the numerator is a group. Okay, here's what I do. I'm going to multiply it by 1. So I'm going to multiply this whole thing by 1. And you're like, whoop-de-doo, what did that do? Nothing. But I'm not going to do one like that. I'm going to do one something like this as a fraction. Isn't 1 over 1 equal to 1 as a fraction? You're going to say, yes, but again, whoop-de-doo, what does that do? Nothing. Unless I make them like this. Ooh, watch. An I on top and an I on the bottom. Because isn't when your numerator is the same as your denominator, isn't that 1? Good. And can't we multiply a number by 1 and not change the value? Yes. So now what does this do? This means I'm going to take I times the group 5 plus 2i, and I'll do that in a minute. But on the bottom, what have I got? I squared. So what do I get on the bottom when I simplify it? Negative 1. There's no imaginaries in the denominator anymore, okay? So now, let me do the numerator. This is going to be then 5i plus 2i squared But what do we say I squared was? What is I squared? -1. So actually, let me kind of remove the I and the sign there, and I'll just make it a negative. And then if I let me just apply the -1 to the numerator. -5i plus 2, and that's kind of backwards. 2 minus 5i. Whew, there we go. Did you lose track of what we were doing? This is the same thing as that. Same equivalent value. It just doesn't have a denominator with an I in it. And it's written in A plus BI form. A is 2 and B is -5. Okay, that's a simple one. How would you do one? Where did it go? How would you do one with a plus sign in the denominator? Oh no, that's even more complicated. What you're going to do is you're going to multiply it by the complex conjugate. What's a complex conjugate? You should know what a conjugate is. It's a binomial that's the same except for the sign on the second term. A regular conjugate would be like A plus B times A minus B. But a complex conjugate says, hey, your second thing's got an I. All right, so what I'm going to do, this is a group, don't forget, this is a group. What I'm going to do is I'm going to multiply it by 1. But I'm going to multiply it by something where the denominator is the complex conjugate to the denominator that's already there. So I'm going to multiply top and bottom by 3 minus 6i, right? Because the sign is plus here, it has to be minus right there. What does the sign have to be in the top? Doesn't it also have to be minus? Because the value of this fraction has to be 1, and so that's 2i. And you're going to say, what does that do for us? Well, multiply it out. Notice I've given room there to work sideways, because when you work with fractions, oftentimes you need to have the rows lined up rather than the columns. But anyway, the denominator really is what's important. So let me do the denominator first. I'm going to have to FOIL this out, or multiply this out. 3 times 3, 9. 3 times -6i, -18i. Okay, now I'm done with that 3. 6i times 3, +18i. Something nice happens right there. If you see that, good for you. If not, we'll come back to it. And then a positive 6i times a -6i. That's going to be a -36i squared. See, I didn't even draw my fraction bar long enough. Okay, that's the denominator. Now let's do the numerator. 2i times 3, 6 i's, like me. 2i times -6i, that would be a positive times a negative is a negative. 6 times 2 is 12, and then I squared. Okay, now I'm going to keep going sideways. Let's clean up the denominator. Do you see that this -18i and this +18i have the same number but opposite signs, and so they cancel each other out and you get 0? Good. But do you also see that this I squared right here can be simplified? What's I squared? -1. Change that sign to a plus and kill the I squared. So really it's 9 plus 36. What's that? 45? Look, the denominator doesn't have an imaginary number at all. It's just 45. Okay? Now, on top, this I squared can cancel, making that a plus. So this is going to be 12 plus 6i. Does anything cancel out on that? Maybe now, since I've kind of got it going, I can read. I think a 3 can factor out. You think? You factor a 3 out of that. That becomes 4 plus 2i on top, right? Divided by 45. And yeah, okay. A 3 can cancel with a 45, leaving me a 15. So I get, here's my intermediate answer. 4 divided by 15, or 4 plus 2i all over 15. Let me split it into the 2 different parts now. I think I'm almost done. 4/15 plus 2/15 times I. That then would be my final answer. Okay? Caution. Let me talk about some illegal canceling here, because I bet somebody up here wanted to do this. Somebody up here wanted to do 12 plus 6I all over 45 and wanted to do this. Oh, the 12 and the 45 cancel with 3. That leaves you a 4 there and a 15 there. So your answer is 4 plus 6I over 15. No. It's all over 45, which means you've got to factor out and cancel the same thing. My little strategy here of factoring it out of the numerator and simplifying is the better strategy. You can't cancel in pieces. And let me show you one more, kind of a simpler example. If I said 4 plus 7 all over 2, here's an extremely simplified version of this mistake, all over 2. Does this 4 and this 2 cancel, leaving me a 1 and a 2? So it's 2 plus 7. Is that 9? Absolutely not. This is a group. Okay, the 4 might cancel with the 2, and it would leave you then 4 over 2 plus 7 over 2, which would be 2 plus 7 halves, but that's not 9. Okay, it's everything divided by 2. The best way to do this is just kind of work it as a group. 4 plus 7, 11 over 2. That doesn't simplify. Be mindful of canceling illegally with fractions. Ist das alles? Oh, yeah, that's it. Okay, boy. Back to me. Whew. Had to use your imagination a lot today, right? Thinking. Thinking's good. And mathematics trains us to think rightly and not accept something as true unless it's been demonstrated to be true. I think what I've done here today is true. If like I've made a mistake in the lesson, which I've done before. People call me out on it. And I find it and I'm like, well, yeah, no, they're right. Mathematics teaches us to think and not to accept something as true unless something's been demonstrated to be true. We should try to do this in other areas. We should try not to accept something as truth unless we've really given thought to it and it's been shown that it is true. But a lot of times people believe what's true simply because they want it to be true. You used to have a word for that. You used to call that wishful thinking. How many things do you and I believe only because it pleases us? I'm embarrassed to say probably a lot. Okay? And that's why everybody should study math, because it's not just useful for balancing your checkbook or sending people to the moon. It teaches everybody how to think, and thinking's necessary, but it's difficult to do sometimes, so be patient with yourself. Anyway, hope you have a great day. Keep pursuing the truth. Bye-bye.